Greetings, Electrophogy here. Today I'd like to talk to you about the field effect transistor. Now, I made a video a while back about transistors, but that was about the bipolar junction transistor. This is the kind of transistor that most people think about when you say the word transistor, because it's usually the first kind of transistor you're taught. The field effect transistor is a similar device. It operates on a different principle, but it's made out of the same stuff. Now, before I go any further, I'll recap a little bit of the first transistor video I made. If you want to watch the whole thing, you can click here. But essentially, they call it a transistor for a reason. The word transistor is short for transforming resistor. That's right, a transistor is just a special kind of resistor. A transistor is a resistor whose resistance value changes based on an input signal, and the resistance value changes transformatively compared to the input signal. Now, by transformative, what I mean is this. Let's say you have some kind of signal input, and if your signal output is the same shape as the input, then it's called a transformation mathematically. Now, as you can see, the function result here is a little bit taller than the input signal. However, it's the same shape, it's not distorted, so we call that a transformation. So, any resistor whose value changes transformatively compared to the input signal, we call it a transforming resistor or a transistor. Now, the field effect transistor was invented back in the 1920s by a physicist named Dr. Julian Lilienfeld, and he invented it through experimentation while working on different types of semiconductors. However, back in the 1920s, they didn't have enough knowledge of atomic physics to accurately understand how it worked. But it did work, and Lilienfeld built some amplifiers and radios out of it, and he showed it to the major radio companies at the time. Now, the radio companies at the time were quite content with their tubes, and because they couldn't quite describe how it worked, Lilienfeld's design basically remained a scientific curiosity, and he never really made any money off of it, but it was patented. Back at that time, they didn't call Lilienfeld's device a transistor because Bell Labs hadn't invented the word transistor until the 1940s, when they invented the bipolar junction transistor. And of course, that made getting a patent a little bit difficult for Bell Labs, because when Bell Labs went to the patent office, Lilienfeld comes strolling up and says, "Hey guys, I hear you've been working on this semiconductor device which changes its resistance based on an input signal. Well, guess what? You're 25 years too late. Who's your daddy now?" Well, after Bell Labs and Dr. Lilienfeld settled their differences and all that sort of thing, they realized that the two devices were functionally very similar, even though they operated on different principles. So Bell Labs changed the name of their device slightly and called it a bipolar junction transistor, and Lilienfeld called his device a field effect transistor. I personally am a simplistic kind of guy. I'd rather work with easy black box models of components so that their functions are simple to deal with. As a result, I try to stay away from talking about the p-n junction, since that involves solid-state atomic physics, and all I want to do is get a circuit to work. However, for a JFET, you really need to talk about the p-n junction because it's fundamental to the concept of how field effect transistors work. So, unfortunately, I will have to delve into the p-n stuff. I'll try and keep it short, since most electronics students have already learned some things about the p-n junction, and much of what you've learned about them is wrong. To keep this video simple, however, I will use the typical terminology that we all know and love, using electrons versus holes, and I will even use electron flow instead of conventional current, which means electrons flow from the negative terminal to the positive terminal, just to keep everyone happy. Let's start with the typical p-n junction. This is what is used in your average diode. The N-region semiconductor is an insulator, let's say silicon, doped with a negatively charged element like phosphorus. So now this insulator has extra electrons embedded in it, and it will now conduct electricity through it. The insulator has been turned into a conductor. The P-region semiconductor is doped with a positively charged element, like boron, which has one fewer electron orbiting the nucleus than it needs to be neutrally charged. This makes the p-type silicon full of holes that electrons can jump into and move around in, so p material is also an insulator that can now conduct electricity. When we apply a positive voltage to the p-type end of the diode, this attracts electrons from the N material, and they go diving into the holes in the p-type material like mice into the holes of Swiss cheese. The electrons go diving into these holes and start going through the p region, and now electrons flow from the negative terminal of the battery through the N region to take the place of the electrons that dove into the holes of the p region. And these electrons then keep flowing through the p region after them and to the positive battery terminal, and more electrons go out of the negative terminal of the battery and follow them. This current flow happens when we forward bias the diode. When we apply positive voltage to the N region, however, we reverse bias the diode, and an interesting thing happens. The voltage potential across the PN junction attracts electrons in the N region toward the positive terminal in the battery, just like before, so they start to flow away from the P material. However, since there are no electrons in the P material to take the place of the ones that just headed out toward the battery in the N material, a small section of this N material near the P material becomes void of available electrons, sort of an electron vacuum. This doesn't mean that the N region now has holes in it. It means that the electron-rich N region has no more spare electrons in that area, so it becomes neutrally charged. This now has been turned back into an insulator. The area at the PN junction where the N region electrons have gone away is called a depletion region. It's an insulator, and no current can flow across it. This is why a reverse bias diode won't flow any current. One other interesting thing about the reverse bias diode, if we increase the voltage of the battery, the neutrally charged depletion region grows wider. Getting back to our original PN junction, remember that both N-type material and P-type material are good conductors by themselves. So it's possible to place two terminals on, say, the N material, and get electrons to flow through it from one N terminal to the other, just like a wire. And this is the basic junction field effect transistor. Electrons flow through the N-type region of the PN device from one terminal to the other, and the name of this N region is the channel. The channel input is called the source, and the channel output is called the drain. Electrons flow from source to drain. The P-type region of this device is called the gate. When there's no voltage applied to the gate, electrons are completely free to flow through the channel, so the source-drain resistance is pretty much 0 ohms. When the JFET is in this state, we say it's saturated. The channel's electron density is at a maximum, just like the base region of a bipolar junction transistor, so resistance is 0. However, when we reverse bias the gate, an interesting thing happens. Reverse biasing the PN junction causes a depletion region to appear, just as it did in the diode, and part of the P and N material is converted back to being an insulator. But now that depletion region causes the physical width of the N channel to become narrower, so less electrons can flow through the channel, which raises the resistance of the channel. As we increase the negative voltage at the gate, the N channel becomes even more narrow, and channel resistance rises further. If we increase the voltage even further, at some point the depletion region will completely block the N channel. No current can flow across the channel, and the channel resistance is virtually infinite. At this point, we say that the FET is cut off, in cutoff state. Many also say that it is pinched off, and the gate voltage that pinches off the channel, called the pinch-off voltage, is around -4 volts. So this is how the FET works. The reverse bias voltage at the gate causes channel resistance between source and drain to increase, and it goes to infinite resistance at the pinch-off voltage. Making the gate voltage more negative than the pinch-off voltage won't cause any further change in the channel resistance, since it's already as high as it can get, infinity. It's in cutoff. One other thing. It's possible to have the channel made of P material instead of N material, and we have a gate made of N material instead of P material. This is called a P-channel JFET, and it works in exactly the same way that the N-channel JFET does, except that the polarities are reversed. Electrons still flow from source to drain, but this time the gate is reverse biased with positive voltage controlling the channel resistance. Now, you may be thinking, hey, this whole thing works by reverse biasing the gate. It's just sort of a diode. Can I forward bias the gate in one of the channel terminals and use it as a diode? Well, yes, you can, but it really isn't designed for that. A forward bias current larger than about 50 milliamps will destroy the transistor, so if you need to use it as a diode, just get a diode. Here's another interesting aspect of the field effect transistor. When the FET's gate is reverse biased, there is a depletion region between the N material and the P material. The depletion region is an insulator, and it's between two semiconductor regions, each of which conduct electricity on their own. So what's another name for two conductors with an insulator between? Well, that would be a capacitor. When you apply a voltage on the gate, the drain current will go to some set value that corresponds to that gate voltage. If you remove that gate voltage, the depletion region will remain there for a while, and the drain current won't change for a little while until this quote-unquote capacitor discharges through leakage current, and the transistor inches back towards saturation, and there's no source drain resistance anymore. This is how dynamic RAM works. A FET is charged up when the computer writes to it, and the computer can then read the value later by checking the state of the drain current. This FET here is essentially 1 bit of RAM. Anyway, there you have it. A bipolar junction transistor is just a resistor whose value changes, and as the base emitter voltage rises, the resistance between collector and emitter drops. Its switching speed is okay, and it's fairly cheap to manufacture. A field effect transistor, on the other hand, is also a variable resistor whose value changes based on input signal. However, as the voltage at the gate rises, the resistance between source and drain also rises. It's a little bit more expensive to manufacture than a bipolar junction transistor. However, its response to changes in input is a lot faster than a bipolar junction transistor, and this is why it's used in computer circuitry. Please click here to go to part 2 of the field effect transistor video. Thank you.